Welcome all. Today we will start another lecture on shared design of beam. So how to design the mainly stirrup of beam. Okay. So let's start. So we will first see the concepts, a little bit concept before we go to the numericals. Okay. So first we have to find out the step 1. Step 1, that is you have to find out nominal shear stress. Nominal nominal shear stress. Okay, so what is this? This is tau vu is equal to vu divided by b into t. So here vu is called as factored shear force. So how will you find out? So vu, the value of vu is for simply supported beam. Okay, for simply supported beam it is wl by 2. Okay, in LSM method the calculation is in LSM method. So the shear factored shear force is wl by 2 into 1.5. This is the factor. So this will be the step 1. So after that we will go to step 2. Step 2 is we have to calculate the tau c max. Okay, so the tau c max is the tau c max means the maximum shear stress. Okay, so max shear stress. So how can we find out? It is given IS 456 table number 20. Okay, so we will see it here. See here, it's given. So this table, maximum shear force tau c max, is given in tau c max Newton per mm square. See, the tau c max depends on the grade of the concrete. For M15, M20, M25, 30, 35 and 40 and above. So it's 2.5, it's 2.8, it's 3.1, 3.5 and this. So from this table we can get the tau c max. Okay, so this is the step 2. In step 2 what we will do, we will check that if tau c max is greater than tau vu, that is tau c max is greater than the nominal shear. Okay, the nominal shear stress. If this happens, then there will be no diagonal compression failure. So there will be no diagonal compressive failure. Okay, so there are two type of failure. The one is diagonal compressive failure and another one is diagonal tensile failure. We will see it later. So next we will come to step 3. Okay, step 3. So what is step 3? We have to calculate the percentage of steel. How to calculate it? It is 100 into A S divided by B into D. Okay, so this is the calculation of percentage of steel, and we need two things: grade of concrete. So by these two things, what we will calculate? We will calculate the design shear strength of concrete. We will calculate design shear strength of concrete. that is tau c. Okay, so everything is Newton per mm square. So from we will get this design shear strength of concrete, from IS 456 table number 19. So let's see. So this is some C table number 19, design shear strength of concrete tau c. So it depends on two things. One is percentage of steel and grade of concrete. So we can get the percentage of steel. See, if the percentage of steel lies say 0.36. Okay, so the value lies between this one and this one. So we have to do uh, then we have to do interpolation. Say for M15 we are finding it out. So the value will lie in between these two value, this value and this value. So we have to do the interpolation. We have seen previously how to do the interpolation. So we have to do the interpolation and find out the tau c, design shear strength of concrete. So this is the step 3. So we will go to one thing we will see here. After we get the tau c, value, what we will find out, we will see that if tau c is smaller than the nominal shear stress. Okay, if this happens, then diagonal tension failure occurs. Diagonal tension failure occurs. Finally, we have to check another thing, that is tau c max, that we get from table number 20. If it is greater than tau vu, that is greater than nominal shear and greater than the design shear strength. Okay, you have to check this thing. Now what we will do, we will go to the step number 4. See, if this condition happens, then we have to design the shear reinforcement in form of stirrup. Design shear reinforcement in form of stirrup. Okay, so here comes the minimum reinforcement. So first we will see what is the minimum reinforcement requirement, minimum stirrup requirement. Okay, minimum shear reinforcement required. So the formula for this calculation is ASV divided by B into SV, that is greater than is equal to 0.4 divided by 0.87 Fy, where ASV is equal to shear area of shear reinforcement area. B is the section, okay, and SV is shear reinforcement spacing, okay, and Fy to we know it. So one thing that is important here, that is let's see here. If nothing is given, how we can calculate ASV? We generally take two-legged stirrup of 8 mm dia. Okay, so how we will calculate it? A 2 into pi by 4 into d square. So it comes out to 100.5 mm square. So if ASV is not given, we will take this value. Okay. So next thing, if there are three types of stirrups. So there are three types of stirrup. One is vertical, one is inclined, one is bent up. Okay. If you see the formula of each stirrup, so here it is VUS. So VUS means the shear force to be taken by the stirrup, to be carried by the, okay, the shear stress to be carried by the stirrup. Okay, VUS. So 0.87 Fy ASV into D divided by SV. So this is the vertical one formula. The inclined one formula is VUS is equal to 0.87 Fy ASV into D divided by SV sin alpha plus cos alpha. Okay, and the formula for the bent up is, so bent up formula is VUS is equal to 0.87 Fy ASV sin alpha. Okay, so if nothing is given in the numerical, which type of stirrup, so we will take the vertical stirrup only. Okay, so now step 4, see, step 3 we have done. So now step 4, is vertical stirrup. Okay, so vertical stirrup calculation, we have seen the formula as 0.87 Fy ASV into D divided by SV. Okay, so ASV we know previously, D is the dimension of the beam. Okay, SV is D is the effective depth and SV is the spacing of the stirrup. Okay, so in mainly in vertical, in stirrup calculation, we have to calculate the SV, the spacing. Okay, so mainly we have to calculate, mainly for stirrup, calculate SV spacing, we have to calculate. See, where VUS will be find out by VU. VU means the factored shear force. See, VU we have calculated it here. VU, the factored shear force, that VU minus tau CBD. Tau C is the design shear strength of the concrete. So you will get it from the table 19. Okay, so you will find out this value, and put it here and find out the SV. You will find out it from here. So see, mainly what is done, if we take a simply supported beam, and it is supported by, this is column and this is the beam. Okay, so the shear force diagram will be like this. It will be maximum, the shear force will be maximum at the support. That value will be WL by 2 and that value will be WL by 2. Okay, so how we will provide the stirrup? So we provide the stirrup. Again we will draw the beam. Okay, again we are drawing the beam. So near the support we will provide, so near the support we will provide this SV value. Okay, we have calculated this SV value we will provide it near the support. Okay, but in the middle part we will provide the SV minimum, that is we will get it from this value. See here, the minimum shear reinforcement, in by using this formula we will get this SV. So the formula is mainly ASV divided by B into SV, that is equal to 0.4 0.87 Fy. Okay, so from here the SB we will give it in the middle part of the beam, as because in the middle part the shear force is negligible. At the support the shear force are maximum, so the SV is provided, the spacing is lesser at the support. In the codal provision in IS 456 one thing is another given, that is this SV we are calculating it. Okay, this SV we are calculating it, and minimum this SV we are calculating it. But there are two another clause that is to be followed, that is SV max will be 0.75 D or 300 mm, whichever is minimum. Okay, so this one or this one, whichever is minimum, we will take that SV into consideration. Okay, so if we can say that by this the SV comes, by this the SV comes to 200. This SV we know that it is 300, but by this formula vertical stirrup formula, we have got the SV say 165. So we will provide the minimum value, that is we will not provide 165, we can provide 170 center to center. Okay, so this is the stirrup calculation, stirrup design. So we are winding up the lecture here. Thank you.